The Routh-Hurwitz criterion is a criterion that tells you when the real part of all zeros of a given polynomial is negative. So, you have a given polynomial p with real coefficients. You know that this polynomial has exactly n zeros in the complex field. Let's denote these zeros by x1 to xn. So these here are the zeros of the polynomial p. The Routh-Hurwitz criterion tells you when the real part of all these zeros is negative by taking a look at the coefficients of the polynomial p. But why do we need a criterion that tells us something about the sign of the real part of the zeros of a polynomial in the first place? Before I will show you the Routh-Hurwitz criterion, I want to motivate this criterion by taking a quick look at the stability of fixed points of differential equations. So, let's assume you have a system of differential equations. So the derivative of x is f of x with starting condition x0. F is a function from x to Rn, where x is a subset of Rn. X is a function from R to Rn. For example, such a system could look like this here. So this is an example for a system of differential equations. A fixed point or stationary solution of this system is a point x bar in Rn, so that f of x bar is equal to 0. So normally you won't be able to find the solution of such a system directly. You're more interested in the behavior of the solution after a very long time, or in other words, will the solution xt of the system converge to the fixed point x bar, or will it go away from x bar in some situations as t goes to infinity, so after a very long time? We call a fixed point x bar asymptotically stable if such a convergence from the solution xt to the fixed point x bar can be shown. Or in other words, a fixed point x bar is called asymptotically stable if the solution xt converges to the fixed point x bar for each starting point x0, so this here is the starting point, in a neighborhood of the fixed point x bar. The idea is now to find a condition that tells us when a fixed point x bar is asymptotically stable. To find such a condition, we will linearize the system of differential equations in the fixed point x bar. So we will linearize this system in the fixed point x bar. So we get a new linear system which acts as an approximation of the original system. So this here is now our new linearized system. This here, df, is the derivative of f. So df is the derivative of f, which is a n times n matrix. We have plugged x bar in the derivative of f. So let's call this matrix df at the point x bar j. Now comes the important part. To find out if the fixed point x bar is asymptotically stable, we have to take a look at the real part of the eigenvalues of the matrix J. We have the following result. The fixed point x bar is asymptotically stable if the real parts of all the eigenvalues lambda of J are negative. We also know that the eigenvalues lambda are the zeros of the so-called characteristic polynomial Pj of the matrix J. Maybe you understand now why the Routh-Hurwitz criterion is helpful, because the eigenvalues are the zeros of the characteristic polynomial Pj. The Hurwitz criterion tells you when a fixed point x bar is asymptotically stable. The idea now is to use the Hurwitz criterion on the characteristic polynomial Pj. The criterion will then tell you when the real parts of the eigenvalues are negative, because the eigenvalues lambda are the zeros of the characteristic polynomial Pj. And the best thing is, you just have to take a look at the coefficients of the characteristic polynomial Pj. You don't need to calculate these eigenvalues lambda. You don't need to find the zeros of the characteristic polynomial Pj. You just have to use the Hurwitz criterion and take a look at the coefficients of the characteristic polynomial Pj to find out if the real parts of all the eigenvalues are smaller than 0, which is a nice thing. Okay, let's take a look at the Routh-Hurwitz criterion now. Let P be a polynomial of degree n with real coefficients, and an has to be larger than 0. If an is not larger than 0, just multiply the whole polynomial p with -1. Then an will be larger than 0, and this will change nothing with the zeros of the polynomial. Let H be the following n times n matrix. We call this matrix Hurwitz matrix. You see, the entries of this matrix H are the coefficients of the polynomial p. You have to fill in these coefficients in a particular way. If the index j becomes negative in the Hurwitz matrix, we just set this entry equal to 0 in the matrix. So aj is equal to 0 if the index j is smaller than 0. Now we have the following result. If all the principal minors of the matrix H are positive, then all the zeros of the polynomial p have a negative real part. So if all the principal minors of the matrix H are positive, then the real parts of all the zeros x of p are negative. The principal minors of the matrix H are the determinant of the submatrices that are situated in the northwest of this matrix H here. So here you have H1, this here is H2, and this here is H3. So you have to calculate the determinants of these matrices here, H1, H2, H3. So the determinant of these matrices here are the principal minors, and these determinants have to be positive. When they are positive, then the real part of all the zeros x of p is negative. So you have to calculate the determinant of all these submatrices here that are situated in the northwest of the matrix. These are the principal minors, and if these principal minors are positive, then the real parts of the zeros are negative. This is what the Routh-Hurwitz criterion tells you. So, in the case of a n times n matrix H, you have exactly n principal minors. Okay, let's take a look at the polynomial of degree 2 now. So this here is a polynomial of degree 2. A2 has to be larger than 0. This here is how the general Hurwitz matrix looks like. The Hurwitz matrix for a polynomial of degree 2 is a 2 times 2 matrix. It looks like this here. So this here is the Hurwitz matrix for a polynomial of degree 2. To find it, we just have to insert here. So n is equal to 2. So this here, a n minus 1, is a1, because 2 minus 1 is 1. This here is n minus 0, so 2 minus 0, so a2. Here we have n minus 3, which is minus 1. And as I have already said, if the index becomes negative, this becomes just 0. And here we have 2 minus 2, so we have a 0. So the Hurwitz matrix looks like this for a polynomial of degree 2. Let's take a look at the principal minors now. So the first principal minor is just a1, so this entry here. The second principal minor is the determinant of h, which is a1 times a2. So a1 times a2 minus a2 times 0, but a2 times 0 is 0. So the determinant of h is a1 times a0. Now the Routh-Hurwitz criterion tells us that the real part of all the zeros of the polynomial of degree 2 is negative if both these numbers, so the first principal minor and the second principal minor, are positive. But this means that a0 has to be positive and a1 has to be positive. So the Routh-Hurwitz criterion tells us that the real part of the zeros of P is negative if the coefficient a0 is larger than 0 and a1 is larger than 0. Because if this is the case, the principal minors are positive. Okay, let's consider eigenvalues now. The characteristic polynomial of a 2 times 2 matrix A looks like this here. So the characteristic polynomial depends both on the trace of A and the determinant of A. So this here is the characteristic polynomial of a 2 times 2 matrix. Now we will use the Routh-Hurwitz criterion. So this here for a polynomial of degree 2 on the characteristic polynomial PA. So we get the following result. The real parts of all the eigenvalues of A are negative if and only if the determinant of A is positive and the trace of A is negative. So this is just this here applied to this characteristic polynomial here. So we get the following result. So the real parts of all the eigenvalues are negative if the determinant of A is positive and the trace of A is negative if we have given a 2 times 2 matrix A. This is very helpful when it comes to stability of fixed points. Let's take a look at an example now. We consider the following system of differential equations, where A is a real number. So this differential equation depends on the number A, which is some real number. First of all, we calculate the fixed points. So we have to solve this here. So x squared minus a times y is equal to 0, and x minus y is equal to 0. From the second equation we get x is equal to y. Now we insert x is equal to y in the first equation and get x squared minus a times x is equal to x times x minus a is equal to 0. So we have just inserted x is equal to y here. Now we solve this here and get the following. X is equal to 0 or x is equal to a, which follows from this here. So the fixed points are n, which is the first fixed point, 0, 0, and m, which is the second fixed point, a, a. Okay, now we take a look at the stability of these two fixed points. First of all, we need the derivative of f, so the derivative of this here. So this entry here is the derivative of x squared minus a times y with respect to x, so which is 2 times x. This here minus a is the derivative of x squared minus a times y with respect to y, so minus a. This here 1 is the derivative of x minus y with respect to x, which is 1. And that here minus 1 is the derivative of x minus y with respect to y, which is minus 1. We call this matrix here J x, y. Now we have to insert the fixed points n and m in the derivative of f. So we get the two matrices Jn and Jm. The fixed point n is asymptotically stable if the real parts of all the eigenvalues of Jn are negative. We will use the Routh-Hurwitz Criterion to find out when the real parts are negative. So we have to take a look at the trace of Jn and the determinant of Jn. The trace has to be negative. So the trace is 0, minus 1, and this is equal to minus 1, and this is negative. The second thing we have to check is if the determinant is positive. So the determinant of Jn is equal to 0 times minus 1, which is 0, plus or minus a times 1, which is plus a, which is equal to a. So the fixed point n is asymptotically stable if the number a is positive. So we get this condition here for the stability of n. Okay, let's do the same thing for the fixed point m. So we have to take a look at the trace of Jm, the determinant of Jm, to find out if the fixed point m is asymptotically stable. So the trace of Jm has to be negative. The trace is 2a minus 1, which has to be negative, so smaller than 0, and from this follows that a has to be smaller than 1/2. And the second thing we need is that the determinant of Jm is positive. So the determinant of Jm is 2 times a times minus 1 minus a times 1, which is minus 2 times a plus a, which is equal to minus a. And this has to be larger than 0. This is what the Routh-Hurwitz criterion tells us. And this here, minus a is larger than 0, is the same as a is smaller than 0. So m is asymptotically stable if a is smaller than 0, because a has to be smaller than 1/2 and a has to be smaller than 0. So both conditions have to hold true, so a has to be smaller than 0. So this is the condition for which m is asymptotically stable. So now you have the following. As long as a is larger than 0, n is asymptotically stable, and m is unstable. When a becomes smaller than 0, then m is asymptotically stable, and n is unstable. Okay, let's consider polynomials of degree 3 now. So here we have a polynomial of degree 3, and a3 has to be larger than 0. This here is the general Hurwitz matrix again. So the Hurwitz matrix of a polynomial of degree 3 is a 3 times 3 matrix. It looks like this here. So to find this matrix here, we have to take a look at the general matrix again. So we have to insert here for the coefficients. So n is equal to 3. So n minus 1 is 3 minus 1, so a2. 3 minus 0 is 3, and here we have 0. 3 minus 3 is 0, so a0. 3 minus 2 is 1, so a1. 3 minus 1 is 2, so a2. Here we have 3 minus 5, which is negative, so 0. 3 minus 4 is negative 2, so 0 again. And 3 minus 3 is 0, so a0. This is how you find this matrix for a polynomial of degree 3. Let's take a look at the principal minors of H now. So the first principal minor is just a2. The second principal minor is the determinant of this submatrix here, which is a1 times a2 minus a0 times a3. The third principal minor is the determinant of H, which is a0 times the determinant of H2. So this here. Now the Routh-Hurwitz criterion tells us that the real part of all the zeros of P is negative if these principal minors are all positive. So this here has to be positive, that here, and that here. Which means a2 has to be positive, a0 has to be positive, and this here has to be positive, so a1 times a2 has to be larger than a0 times a3. So we get the real part of all the zeros of the polynomial P is negative if and only if a2 is larger than 0, a0 is larger than 0, and a1 times a2 is larger than a0 times a3. That means that all the principal minors are positive. Let's take a look at the eigenvalues of a 3 times 3 matrix A now. So here we have a 3 times 3 matrix A. The characteristic polynomial PA of this matrix A looks like this here. PA depends on the trace of A, the determinant of A, and the coefficient k. This coefficient k here can be calculated the following way. K is equal to the sum of the determinants of the following submatrices of A, this here, and that here. Okay, now we can apply this result here on the characteristic polynomial PA. So we get the following result for the eigenvalues of a 3 times 3 matrix A. The real parts of all the eigenvalues of A are negative if and only if the trace of A is smaller than 0, the determinant of A is smaller than 0, and k times the trace of A is smaller than the determinant of A, where k is this value here. So to get this result here, we just used this here on the characteristic polynomial PA. This result here is again especially helpful when considering the stability of fixed points. Okay, I hope this video could show you that the Routh-Hurwitz criterion is especially helpful when taking a look at the stability of fixed points. The idea is to use the criterion on the characteristic polynomial Pj to quickly find out when a fixed point is asymptotically stable. If you think this video is helpful, please consider subscribing to my channel. It would really help me to keep creating videos.